Okay, welcome to the CZO seminar. We moved it to Mondays so that we can get different people who can't come on Friday. So that's why we're at a different time. We'll try to keep doing it at different times because we miss the same people over and over again when we have it on one time. So a couple announcements. The all hands meeting is all day May 11 and May 12. It's different than we've organized it in the past. We tried to intersperse conversations with talks and posters throughout instead of having all the kind of introspective conversation at the end. So look at the schedule when it comes out. Have you sent it out to everybody? You waiting for the abstract? Okay. We should send out the agenda. We can send it out before the abstract call, but make sure everybody looks at it and make sure they get it on their calendars, okay? We need one team member from each hypothesis group to participate in the field trip. We also have talks by each hypothesis group, and we're almost 100% insisting that the talks be by students. Now, of course, there could be a reason your student could be out of town, your student could be, deathly ill or something, I don't know, but we really want the talks to be given by students to the extent that we can have that. Now, there will also be posters. Anyone can do a poster on top of a talk, or any person that's not giving a talk can certainly do a poster. And then Ting has been organizing the postdocs and grad students to have some group posters, which we're kind of synthesizing data. So we're very excited about that. Are there any questions about the all hands? Okay. The abstract call will go out really soon. For the people that are giving talks, and even for the people giving posters, you should think about it as a talk or a poster about what you've accomplished, but with an eye towards what would be cool to keep doing. So this all hands, the reason we kind of reorganized it was to try to get everybody thinking about the renewal, which we're going to have to write in the next 6 months as soon as we see an RFP. So think not only about what you've done and package what you've done, but also the future. We're going to have a catchment cleanup, and it'll be the week of May 1st. And Brandon's going to get those days out. Brandon was in a car accident this week, so he's recovering. We're glad to see you back. Doesn't look completely happy over there. Yeah, still pretty sore. Somebody hit him, so it was kind of a serious accident, but I guess he's back, so we're very pleased about that. So the cleanup will be that week of May 1st, and the date will go out. Every team has to have people show up. We also got a car, which isn't on here. So we are now leasing a field vehicle. Anyone who's over what age? Anyone over 21 can sign up for it. There's an online place to sign up. Brandon sent some information out about this. Brandon will be making sure that, we don't have people fighting over it or whatever. Anybody that breaks the rules with it or whatever, obviously that's going to be a problem, wouldn't be able to use it, but it's a way to help people to get out there without having to use their own vehicle all the time. And it'll be in this parking lot. Okay, and what is it again? The Jeep Liberty. It's a Jeep Liberty. Okay. Yeah, the back seats will lay down flat. I'm just doing it in the microphone. You can take 4 or 5 people, however many seatbelt sets are out there. Registration for the June Arlington meeting. This is the National CZO meeting. As far as I know, anyone can go that wants to go. We will have to pay for travel, but that's hardly anything to get down to DC. The lodging is going to be paid by the National CZO. Now, if there's too many people sign up, we may end up being told that we have too many people, because I know lots of people from Shale Hills have signed up. But by all means, sign up. By all means, register. You can put up a poster down there. We're really looking for non-CZO people to go as well. So if you have non-CZO friends, people that you think would be interested and have professed interest at other institutions especially, or even here, by all means, invite them. Professors, postdocs. We're trying to get as many people down there as possible. It's right next to NSF. So we're really trying to make sure that it's a good interdisciplinary group. Any questions about any of those things? Okay. The next seminar is April 24 at 4. It'll be over in Forest Resources Building. And I think that is going to be Dan and Brandon talking about instrumentation and data, but it's also going to be the time where we can talk about what field work is going to be happening this summer and kind of get ourselves coordinated. So that's like we do this every year, sort of our coordination. It'll also be the last meeting before all hands, so if we have any coordination. Okay, any other questions? I don't know, I haven't heard anything about an RFP from NSF. I think they're waiting for this Arlington meeting before they put out an RFP, but they must be writing it already. No one really knows what's going on. Questions? Okay, so I'm going to turn it over, I think, to Dacheng, unless, is Lili saying anything first or anything? Goes right to Dacheng. Okay, so Dacheng Xiao. A lot of people see.
Hello. Okay, it should work now. And it will also balance the ecosystem. And the global water cycle is also highly related to lots of hot topics we are concerned. For example, the global warming, the chemical weathering, nutrient export, groundwater potential, etc. Oops. Yeah, thanks. So the watershed is a fundamental unit of the whole global water cycle. In a watershed, the water comes into the watershed from the precipitation, will be intercepted by the vegetation, form the surface runoff, or infiltrated into the subsurface and form the unsaturated zone and saturated zone. There will be a recharge between these two zones. And under the solar radiation, there will be a snow melt and evaporation from the open water, from topsoil layer, from canopy, and transpiration taking the water from subsurface by the vegetation. Finally, the water from subsurface, surface runoff and subsurface lateral groundwater flow will become discharged and goes out of the system. So you can say this is a complex process, a complex system. It is very important for us to understand what controls those processes to better help us understanding the whole system. So when it comes to the controls of water hydrological processes, people found that the topography will influence the slope, which will change in the water potential gradient and leading to different water fluxes from ridgetop to the valley flow. And the different aspects in the topography will receiving different solar radiation and turns out different evapotranspiration. When a watershed with different vegetation, the vegetation actually different soil, different root structure and the leaf type from different vegetation will change the canopy evaporation and will change the transpiration ability. So we could get different evapotranspiration caused by the vegetation. And the root will generate different pore structure, which changing the hydraulic conductivity in the subsurface. Then how about the lithology related part? the lab and the pilot scale tests have been done to find that the soil and rock properties can influence the hydrologic processes like properties like water storage, the hydraulic conductivity, different soil layer depths by different chemical weathering rate, and also the joints, fracture, macropore, something like that. And when it upscale to a watershed scale, people, the water-related processes where the work have been done, like the solute injection experiments, the alluvial fan fishes study, or the chemical element concentration studies. However, there is lack of study on lithology control of complex hydrologic processes at watershed scale, especially for the watershed comparison study with similar condition in other factors like the land cover, the climate condition, and the upstream conditions. So in order to fill this gap, we try to answer a question. The overall question is, how does the lithology influence the hydraulic processes across two monolithology watersheds? We got very lucky because we have Shale Hills and Garner Run provide a very good study resource for us. They have actually they have the same land cover. Both of them are forest watershed, and they are all located in the central Pennsylvania. So the climate conditions similar, and both of them are first order watershed, which means they get the same upstream condition. The major difference between them is the lithology. One is dominated by shale, another one is dominated by sandstone. And they will have different silt clay percentage, different roughness, and different soil layer depths. We already, so to compare this two watershed, we try to use a model as a major tool, combining the data from national data sites and the field measurements, censuses together, and get some information about the processes, about parameters, about our understanding of lithology. We already have a hydrological model developed in the Shale Hills based on intensive measurement data. So we want to get the benefit from that work and try to do less work and compare this to watershed. So the first sub-question is, can we use the calibration obtained from one watershed, the Shale Hills, in another one, the Garner Run, without recalibration? And say, can we predict the watershed without any field knowledge? And if we can't, if the model still need calibrate, what soil-related parameters will change during this transform, and how do they change? Finally, we will come back to this overall question, the lithology control of hydraulic processes. The major tool we use is, model tool is FluxPin. It's combining the Penn State integrated hydrological model and the NOVA land surface model together as a physics-based spatial distributed model. It can simulate the processes like infiltration, the evaporation from soil, from canopy, transpiration by the root, and the vertical flow in unsaturated zone, the lateral groundwater flow, horizontal flow in saturated zone, and the recharge. Based on the heat balance, the energy balance, it can partition the soil moisture in different soil layers. And the first part is can we do the prediction without any field knowledge? Can we develop a model directly based on the national data sites? So to answer that question, we developed the Garner Run's model only based on the Shale Hills model calibration information and the national data and the data from national data sites. Here is the results of some water variables. This is a flux discharge in the outlet of Garner Run. The red dashed line here is the model results, and comparing with the blue solid line measured by measured in the field. What we found is from the trend of curve, we can say the model can have can capture some water events like snow melting, large discharge happening in the rainy season. However, from a hydrologic perspective, if we calculate some statistic criteria value, say net surface efficiency number, this number compare the simulation and the mean value calculated directly from the observation, compare these two values, and it is a number less than 1. If this number larger than 0, which means the simulation is better than the just use the average value of observation to estimate the discharge in a watershed. The closer to 1, the better performance. However, our number is -1. So which means actually it is not transferable. Actually, we also found we will underestimated the discharge in dry condition, and we cannot capture lots of peaks. If we look at the soil moisture, again, this red line is the simulation. The blue one is the observation. This is the area average, the soil moisture coming from Cosmos. We can say, although the statistic criteria number seems not bad, but we were missing lots of things. We cannot capture the observation, especially during this dry condition. Just like we will overestimate the soil moisture and underestimate the discharge. So in this case, we will say from sandstone, from Shale Hills to sandstone to Garner Run, what we did, the calibration fail we did in Shale Hills is not transferable. So we need to recalibrate the model. The things is, we are thinking when we get a calibrated model, we can find some calibrated parameters there. Compare those parameters with what's happening in Shale Hills. The difference can give us some information. This is the basic idea. So we want to say what will change and how do they change. The approach of calibration, or say the parameter estimation, is shown below. After a pre-screening by a first-order sensitive analysis, we picked up those 6 parameters: the Van Gunacton alpha, beta, porosity, megapore depth, saturated hydrologic conductivity of megapore in both horizontal and vertical direction.
So where did those 6 come from? Is that from Yuning's work?
From both Yuning's work and first order sensitive analysis. I have a backup slides if we, yeah. And we have 2 cases for the Garner Run calibration and the different soil condition. I will talk about it later. For each case, I sampled 500 parameter sets by the Larkin hypercube sampling method based on a prior distribution, the prior range. Those ranges coming from the literature and our experience. For example, the beta will give a prior distribution with a range of 0.9 to 1.8. There are 500 runs. And we put those runs to the FluxPim model, run the simulation and get the model results, compare it with the data, and calculate the statistic criteria value. Compare those values with the standard criteria. If you're sampling 500 parameter sets, where are you sampling them from? We give a prior range for those 6, each of those 6 parameters based on the literature and our experience. And during that range, we're sampling different parameter value.
So each parameter has a range, right? And then let's say you pick in that range, you sampled maybe 6 numbers for alpha, 6 numbers for beta, and then together in 5 cases, running cases.
So he has a range for alpha and a range for beta.
Yeah,
So he
there
puts
is.
6 things within that range.
Yes.
6 in beta, and then he would have 36 things to try, but he's got 6 things.
Yeah, so we have 500 alpha, 500
So
beta.
matrix of all possible parameters.
Yes, yeah, to search in the parameter space. Yes. So if the our model data comparison can satisfy the standard, we will say those runs are accepted runs, and we use that run to evaluate the estimate of parameter. You can say.
I still don't understand because you also have positions on your watershed. So you've got like 500 parameters and however many positions on your watershed. So how did you do that?
It's like this. For each of these parameters, in one case, we have 500 value. And for both these 2 cases, we have 1,000 runs. Each run, we will have a different value of alpha, beta, porosity, those 6 parameters.
What about all the spatial stuff?
Oh, spatial. For the spatial variation, we will keep the map. Maybe coming from for example, the soil property coming from the SSHCZO database or coming from the field macropore measurements. For the land cover parameter, it will follow the basic relationship from the land cover datasets. So the map is already coming from the national datasets, but the exact value, the value level will change.
How many triangles do you have over your whole watershed?
For Garner Run, we have more than 500.
Okay, so you have 500 parameters and 500 sites. What do you do with that?
It's actually for here we keep the relationship of the spatial distribution of parameter.
So
the only change.
Numbers from the circle, let's say, already spatial variation.
So he has values for all of us. He doesn't have macro.
From circle, yeah.
He doesn't have macro for you.
How do you get my?
The macropore, for example, the macropore conductivity, we have a relationship between the matrix soil conductivity. That is a base, that is a basic. We will give a multiply to those map-based parameters.
So you get alpha and beta from SSHCZO.
Mm-hmm.
And then you have a rule, an equation from which you calculate macropore K from alpha and beta or something like that.
Yes, yes.
And that rule comes from whom? Who gave you the rule?
Oh, the rule based on the literature, we built a relationship. For example, one has a larger metric soil. They believe it will have a relatively larger macropore.
So it's a circle, so the relation is from circle?
No, from
literature?
No.
Not from macropore.
From literature.
Yeah.
Okay. So there is a spatial distribution of all these parameters, and he keeps the spatial relative value of each the same. So every time he changes, it's changing proportionally to each number. Like let's say he has a.
Doesn't SSHCZO give you the porosity of the soil?
Yes, it has a reference value. Yes. Yeah. Okay. So for example, the beta, after those accepted tests, we will get a new distribution, new range of this data. And we use this new distribution to evaluate the estimate. We take the mean of that distribution as the estimate of each parameter. And this is our study case setup. So because we believe the major difference between 2 watersheds is soil-related one. So what we changed is the soil-related parameters. Let's say for the first case, we use only the soil information from the SSHCZO datasets. But for the case 2, besides the SSHCZO soil map, we will add the field border map into the map. Then we will not only have the metric soil information, but also the border fractions. For example, blue in 10% and green in 40, between 10 to 40, and yellow, green in 40 to 80, and the yellow orange larger than 80%. So in the model, actually, we change the macropore fraction based on those border map in order to represent those exist of border. Here, I showed the satisfactory range we choose for different statistic hydrologic criteria. And you can say for each of case, we will have 500 runs, and those number is the runs that satisfy the corresponding criteria for discharge and soil moisture. And those one is for example, the case without border map, we have 19 accepted run that can satisfy all the criteria. So finally, the overall accepted runs we got in this study is for each case is less than 20 number. And compare with this total 500 for each case, actually there are a huge number of rejected sets of parameters.
So I kind of understand what you've done, but when you bring in the boulders, I don't understand.
Okay.
How do you put an alpha beta for those?
Oh, for example, in this boulder case, we don't change the alpha and beta directly. Especially the relationship of the alpha here and alpha there, we don't change that relationship. The only thing we change for boulder is we change the macropore fraction defined in the PAIN model. So that fraction.
Do that ad hoc.
Yeah, we can do that. And follow.
You're just making it up, right?
Yeah.
Do you have a systematic way to do, like how did you add this information on the folder?
For example, in the soil properties, there is a macropore fraction parameter. So for the case one, if we only have circle soil map, we will keep that fraction as what we found in Shale Hills. But for this second case, for example, different location will have different border fraction. Larger border fraction, we believe there will be a larger macropore fraction. So
Sue, this was based
I'm trying to understand what he did. I understand what you did. I'm trying to understand what he did.
Okay, I was going to say the numbers weren't made up. That was like the
No,
percentage.
I know you was. I totally understand what you did. I understand the math. Then he takes the math, and I think I kind of understand what he did with Sorgo. But now he's got something new for which he has no information other than that it's either boulder or not or tree or whatever.
yeah, actually.
So there's some rule he's used that, as far as I can tell, you just pulled it out of thin air.
I have an attribute file for each element, for each location. There is a parameter called macropore fraction to define the macropore fraction in the whole metric soil. Those maps gave me information about that fraction number. For example, smaller border fraction, I gave a smaller macropore fraction. And I keep the ratio of those 4 different types.
You kept the ratio.
Yeah, keep the ratio.
So conceptually, consider these boulders are met.
Yeah.
And then you
So
say
it makes the fraction higher for the
Yes.
price of the ratio.
Yes. Okay, thank you. Okay, then here is a prediction of accepted runs. You might remember we actually, in the transferability test, we actually miss some peaks during this rainy season, right? And we cannot capture the peaks and will underestimate the discharge for those 2 periods. And for the soil moisture, again, we will overestimate those parts during the dry condition. But this time, if we look at the calibrated prediction, we can say those problems have been solved. We got those small peaks during the small rainfall event and not underestimate those parts, and those peaks follow the good trend.
So this was one of the 19 runs that worked.
Oh yeah, you can say the green one is the range based on that 19 runs. And the red one is the mean of that 19th class. And if we compare this case 1, the without border case, and the with border case, we can say, for example, if there is a rainfall event, not that much, we will get a sharp and narrow discharge peak, which means the border case actually have a lower water retention ability that make the water goes out of the system quickly. So you can say we don't have this lag in the border case, and we can capture this observation here and here. Basically, we thought those calibration is successful, and we can use that to do more hydrological processes analysis. What if this is a accepted runs? What if we show some rejected one?
Yeah, so for which discharge, this is like the oldest discharge data set.
For this part is the new one. You might look, this number is smaller than the previous one because I use the daily average number, which means I divided the largest one by 24, so it's smaller in this case.
The peak flows in your whole time series look lower.
Yeah, yes. Yeah, but this is, I didn't use the one before June because we have lots of uncertainty there. Yeah. What if we look at the rejected runs? I just picked 10 of them as an example. It will be very chaotic. It cannot see anything from those rejected simulation. In these aspects, we want to recall another question. We mentioned that the transferability test is not good, cannot transferable, but it is also still have some important information. You may remember the shape of the transferability discharge, although it has some difference, but it at least can keep the basic level and keep some trend. So we believe that is the advantage of the physics-based model. And here comes to the parameter comparison.
Can you quantify how good your model is? Like
Yeah.
You showed us this MSC, but did you show it?
Yeah, for all those accepted run, it can satisfy those 6 criteria. For example, for discharge, the NSC number, all of them are larger than 0.3. And the BIOS percentage, all of them is less than 25%. And for the RMC observation standard deviation ratio, all of them is less than 1. So we based on some hydrological study and to make those criteria range.
And then
All
there's no reason to choose with or without boulders.
Those criteria is using for both cases.
Can you tell me whether it's better to run a model with boulders or without boulders?
I will say it later, but yeah,
You will say later?
yeah.
Well, okay, so we can wait till later then.
But yeah, basically the boulder map can give us more information, especially to deal with the spatial distribution. And I have mentioned, for example, here, if we don't consider the boulder, we will have a lag of simulation for those cases. But in this one, we can capture that. And for some other small peaks, I think the boulder cases is better than without that. And here has another information of using boulder. In this figure, the black cross represent the Shale Hills parameter for alpha, beta, porosity, 6 of them. And the red square is the Garner Run without boulder. The blue circle is the Garner Run with boulder map. Let's say from Shale Hills to Garner Run first. We will say the Garner Run has a small alpha value. If we consider the physical meaning of alpha.
Average for the whole watershed?
Yeah, this one? Yeah, basically we already have a relationship inside the circle. So all of this is the averaged value of the spatial average value for all the accepted run over the whole watershed. Yeah. So the Garner Run has a smaller alpha value. Consider the physical meaning of alpha. It is inversely proportional to pore diameter. So, which means Garner Run has a larger pore diameter. And for the beta value, the Garner Run has a larger beta. The beta is inversely, it's a fitting parameter, which is inversely proportional to water retention ability. So we should say Garner Run has a lower water retention. So the water in Garner Run will go downslope faster than water in Shale Hills. As for the porosity, the Garner Run's porosity is relatively larger, which means the water storage generated by the porosity in Garner Run is larger than Shale Hills. And if we consider those three macropore-related parameters, the macropore depth in Garner Run is smaller than what in Shale Hills. This parameter is highly related to the soil layer depth. So the smaller one in Garner Run, actually, we guess is because of the, we know the sandstone watershed has a slower chemical weathering rate, which generates a smaller soil layer depth. And if we consider the conductivity, the overall conductivity, the Garner Run, this is magnitude larger than Shale Hills. And it's larger than what in Shale Hills, which means we think that is caused by the preferential flow generated by the.
How does SSHCZO define their macropores? Does that include fractures or is that just soil?
Basically, SSHCZO don't have that information, but in order to, but in order to consider that parameter, that processes, influence of that processes to the model, we have some default value there. We will, after the calibration, actually that value have been calibrated, have been tuned to a range that we think is acceptable.
And neither run have fractured bedrock as a layer, correct?
No.
Right. So it is
No.
it's just soil and
Just the
bedrock
soil.
is like a lower bound. It's like,
Yes.
I guess I'm down. I'm surprised by the macropore depth being lower than at Garner. But it might be because it's
definitely slower or deeper.
Didn't you say, so you said the macropore depth at Garner Run is less?
Yes, less than what in Shale Hills. Yeah.
It's a little surprising.
So he's saying that it's equivalent to the soil depth, and he's saying that the
So
soil
it's
is.
only in that soil.
That's what he's saying.
Yeah. We still need to do some groundwater, take groundwater as constraint to check this parameter. This is a preliminary conclusion. After we tune that with groundwater, we may get some new idea of that.
Are these values just for the soil layer?
Yeah, just for the soil layer. From the hydrologic time scale, from hydrologic perspective, we focus on those perched groundwater for this study. Yeah, that's a limitation. And if we consider the case between the comparison between two cases, for example, now if we're moving the case with boulder map to without boulder map, what could be found? First of all, we know between these two cases, we change the macropore fraction a lot. And those three parameters actually are highly dependent on the macropore fraction. So it is hard for now to tell the relationship of those three parameters. But we can also find some interesting results in the soil, matrix soil properties. For example, from the one with boulder to the one without boulder, we need to keep the trend of changing the Shale Hills to, of changing that from Shale Hills to Garner Run. What does that mean? That means if we moving to the case without boulder, we need a smaller alpha to pretend they have a larger pore diameter. And we need a larger beta to pretend there is a macropore where there has something that make that has a lower water retention ability. So this means after the calibration, the model will tune themselves to pretend the macropore existed there. So our conclusion here is we can find the macropores in solution. If we consider the border map in the model, we can get a parameter close to their physical meanings. And here, we actually we normalize the parameters based on their perturb range and based on the reference level, the mean of all those value. And then we get the relationship of actually get a range of all the accepted run parameter compared with the Shale Hills one. From those figure, I would say the smaller range, the more sensitivity, which means we only have those small range for porosity to be accepted, for porosity value to be accepted. Means porosity is very sensitive. The same as beta, the same as those other parameters. And no matter it considered border or not, actually those kind of sensitivity doesn't change. So from this result, and also based on Yunin's global sensitivity analysis, we conclude that the Van Noten alpha, beta, porosity are most sensitive parameter in the system. For now, we have those information from Circle. If this map is not good, or if there is no available data from the data sets, then the field measurement or the lab experiment on those parameters are needed. And the final part is we use this calibrated model to predict water behavior and to compare those two watersheds. This figure is applied the model in same precipitation and LAI condition for both sides. For example, we keep the precipitation and LAI from the Aneldas and the Modis during 2015, apply that to Garner Run and Shale Hills at the same time. We normalize the discharge data, and in those figures, the green line is precipitation. The red circle is the measured discharge data, and the blue one here is the surface runoff. The red one behind the blue line, the red line here, is the total discharge from the model. And the subsurface lateral groundwater flow is the blue line. So from this, it tells us several information. First of all, we know between the comparison of data and the model results, we can say after the calibration, we can already pick lots of the hydrologic behavior of the discharge. And if we look at one rainfall event here, there will be a surface runoff quickly, and then it will followed by the lateral groundwater flow for a longer duration. And if we look at the trend here, basically the surface runoff keeps the change of basically the change of the precipitation and the snow melting event. But the lateral flow, not only based on those, and also we will say a relatively lower condition during when we have a higher evapotranspiration. So the lateral groundwater flow are controlled by both precipitation, the temperature, I mean the radiation of snow melting, and also the evapotranspiration. If we compare the Garner Run to the Shale Hills case, except those snow melt season, because this is already normalized discharge by the area, so we can compare them directly. We can say the Garner Run actually has a relative higher number than Shale Hills, which means discharge than compared with Shale Hills.
So it has higher discharge, normalized.
During except those snow melting season, during those part, during the rest of the season. This is constant with what we found, that the Garner Run has lower water retention ability, so the water will goes out of the watershed quickly. And we have another interesting finding that you can see the ratio of the surface runoff to the total stream discharge in Garner Run is smaller than what in Shale Hills. Right? We will discuss it soon later.
So you can ask a question.
Sure.
So in the last plot, the Garner Run, so the Q sub D is the modeled discharge,
Yes.
and that's completely behind the Q sub L.
Yeah. You can think that those red line is it's the summation of green and blue line. Green one is very small, so.
Okay, so it's saying that all the flow is from lateral flow.
Most of them. Yeah, I will discuss it later, soon later. It's yeah. And
Can we just stare at that slide a little bit?
sure.
So Shale Hills has more QS than Garner Run.
Yeah, it looks like this.
That's runoff,
It's surface runoff.
surface runoff. Yeah. So there's more surface runoff at Shale Hills than at Garner Run.
In this case, because for this case, the Shale Hills calibration data is based on the circle one, it might be a little bit different with our field measurement. But even that, we can, I think in the later discussion part, I can tell our guess of what those happen, the larger surface runoff happening in Shale Hills compared with the. Okay. Then we can discuss that first. So this is the ratio we just discussed. We found that the Garner Run has a smaller ratio than Shale Hills. We think there are two reasons. One is infiltration rate.
Kind of going too fast for me. So QS to QD, that's the surface runoff
To total stream discharge. Yes. Okay. We think there are two reasons. One is infiltration related. You can say the Garner Run has a small surface runoff. And from Jean-Marie's field experiments, she also found in Garner Run, when we have a big boulder, the water will infiltrate it into subsurface quickly, right? So we think that is one reason. The Garner Run has a larger infiltration, and then it will have smaller surface runoff. Another reason is we can see the topography influence here. The Shale Hills only have a very shallow valley flow from the topography LiDAR data. But Garner Run, at the Tercey Mountain site, there is a gentle slope region, right, in the valley flow. That region, I think it is a buffer that can receive the water from the hill slope and slow them down, give more time to infiltrate it into the subsurface. In this way, more water we found from the stream will be coming from the lateral flow, other than from the form of surface runoff directly. This is why we found those strail.
You said that the soil depth is smaller in Garner Run than Shale Hills. But down in the valley, there's pretty thick sediment fill. Are you just ignoring that? Because now you're kind of talking about that area. And don't we think that the water goes down in there, and isn't that like hydrologically active, that valley fill?
For now, actually, for Garner Run, I keep the same bedrock depths for the spatial distribution. So I think, yeah, that's a very good point. If we consider more soil there, we will that domain will be able to receive more water and cause those after calibrated results there.
So soil depths are all the same.
For Garner Run, yes.
Do we have new soil depths?
So,
Like
Wait, I thought you said that the macropore depth was related to the soil depth, and that's why you made it lower in Garner Run than Shale Hills.
between sites.
yeah, between the Garner Run is less than Shale Hills, but the Garner Runs, there is no spatial distribution.
Right. So right now, as Dacheng's explaining, his model runs uniform bedrock or uniform soil
layer.
thickness, but the soil macropores are spatially variable depending on the map.
Yeah.
We definitely have, from the shallow geophysics, sort of clear first order observations that on the steeper hill slopes, we have maybe 2, 3, or 4 meters worth of mobile regolith. Then there's a layer of fractured bedrock, and then there's a layer of sort of much more competent bedrock. In the valley fill, we have shallow seismic tomography that tells us we have about 10 to 15 meters worth of sandy clay-rich fill, and that's not probably a fractured bedrock layer. That is much like what we saw with the core, real thick, just like junk sitting in there. And as Sue mentioned, if you go down the valley, that low sloping, fine grained bench does indeed have like perched aquifers with channelized surface flow on top. So it's a mildly complex layered system down there in the valley fill. Yes.
So you will see the huge between the valley floor and ridge top soil depths. Huge difference in terms of soil depths.
And that's much deeper.
Yes, and the nature of the contact between the soil and the solid bedrock is very different on the hill slopes versus in the valley fill, because we know on the hill slopes that there is this layer from the ground penetrating radar has shown us that there is a significant layer of bedrock that has been fractured because we get reflection. We get reflectors off of it, but they're tilted as if they were in sort of the bedrock position. So we know that there's a fractured bedrock layer up on the hill slopes. We can't see that in the seismic tomography. It may or may not be in the valley floor, but what we do see in the valley floor is at least 10 to 15 meters of debris fill. That's sandy, clayey.
Can we call that soil?
Well, that's, yeah, like, I don't want to call it soil, that's fill. I mean, it's
Okay.
not pedogenesis,
The
right?
real question is, should it be in your model, right?
Yeah,
Because of
yeah,
the
that
law,
should
right?
be, yeah.
I mean, if it's hydrologically active, the water would be done model.
We just have no idea what happens in subsurface at all in terms of the water flow paths. I don't know if it holds water, I don't know if it fluxes water more quickly, I don't know.
Yeah, that should.
I mean, is it in your soil map, just for now? Because I mean, if Survey was taking force under, right, they would have that as their soil, just a sandy.
It has,
So it's probably
yeah, but
already incorporated in your modeling.
As a type, but not the depths. Right, so it doesn't give you depths. Right?
no,
So
that's.
yeah, so down,
It doesn't.
right, so down the valley, where the Garner Run stream cuts through this fill, so it exposes about 1 meter or 2 meters of this fill.
Uh-huh.
And you can very clearly see you've got about half a meter of clay sandy fill sitting directly on top of a boulder lag. So it's a big pile of boulders, but because that clay is sitting up there, it actually perches overland flow. And it's really, I mean, I have no idea if that's happening in our part of the watershed, but it would make sense that would be, for just one example of how complex the subsurface flow could be in that valley fill.
Yeah, so the key is like, how is the distribution in terms of permeability in the vertical direction? Where
It's
because P mostly capture the shallow. So
Yeah, the perched one.
Yeah.
Yeah, but we do find there will be more water goes into deep groundwater. If for now we have a bottom boundary, if we remove that, I believe there will be more water goes into the deep groundwater. Yeah, at Shale Hill, at Garner Run. Yeah. Okay, then maybe I can just talk about those parts. Based on those slope, the gentle region, we also find a relatively larger area of soil moisture with larger soil moisture in Garner Run. This is why we think after the calculation, we found the larger evapotranspiration, because larger soil moisture here provide a chance to the vegetation take the water in subsurface out of the system.
And the reason there's higher soil moisture is because of the break and slope on the north side?
Yeah, that is. Okay, and let's go back a little bit. We also compare the circle soil map and the border maps soil moisture, the spatial distribution. What we found is with the border case, the soil moisture in this gentle slope region is relatively smaller than this case without border, and we'll have more water, soil moisture around the river. If it is hard to look those two figures, we can say this water loss figure. Those parts, if we compare the border fraction map, where we have larger than 40% part, they will have more water lost caused by the preferential flow and the lower water retention ability. So this is for take-home message. We think that from a hydrologic perspective, our work found that the transferability is not good from Shale Hills to Garner Run. But yeah, it is not good. So if we want to get a better prediction of the model, we still need to observe the discharge and the soil moisture to recalibrate the model in a new set. And we also found the alpha beta porosity are most sensitive one. If the data size, national data size is not available, we need to measure them. And compared to lithology watershed, we found the sandstone has larger pore diameter, larger water storage caused by the porosity, and the lower water retention ability, shallow soil layer depths, and the larger preferential flow. The topography, especially the gentle slope region in Garner Run, also influence the water behavior. For example, it will change the contributions to stream discharge and also change the water balance. The border map can help us get a parameter estimation close to their physical meanings and get a better spatial distribution prediction of the water variables like soil moisture, groundwater. And finally, we believe the approach used in this model data synthesis study can be applied to other watershed comparison cases. For example, a dry watershed compared to a wetter one, or the forest compared to the farmland, say Shale Hills and Coal Farm. That's all we have today. Thank you for your attention. Any comments and questions?
Can you explain again how you got to Garner Run having more preferential flow? Are you getting back and forth?
Oh, yeah.
Can you repeat the question?
Oh, okay. Best question is why I can identify the Garner Run has more preferential flow. Right? So there are two. I think there are two things that I can say. One is from here, based on the parameter itself, because parameter has a physical mean related to the hydrologic processes. The megapore hydraulic conductivity, if we calculate the overall influence, we will say it has larger because this is a magnitude larger than Shale Hills, and those is a smaller one. If we do a calculation, then the Garner Run has a larger conductivity properties. So which means it has more space or transportation ability than can moving water out. That is one.
Would you say that's because at Garner Run, the preferential flow is, I guess, more widely distributed everywhere in the catchment, and at Shale Hills, you may have more concentrated preferential flow and it swales?
Yeah.
Can you repeat the question?
Best question is, does that mean the Garner Run has more preferential flow over all the watershed, but Shale Hills only have the preferential flow in the swell? Basically, the Shale Hills has the water in swell, the preferential flow in swell. From my study, I couldn't tell the reason, but from Harry's study, they believe there is preferential flow. In Garner Run, from our results, we just compare the overall parameter, overall macropore hydraulic conductivity properties. We can get that results. And also, if we compare those case without border and with border, you can say the with border one have less surface runoff, which means more infiltration. That keeps with the macropore's preferential flow in vertical direction, right? And each well has larger discharge.
Is the difference so small? Do you really believe this?
So I think those, yeah, it is small, but it has those differences. I think those buffers region will somehow decrease those influence between two cases.
I think what you were talking about is that the one without border map already kind of adjusts itself with certain parameters to capture the micropore effect. Right. He was when he talked about these parameters, the differences between with and without. Yeah. I think some of the messages he is essentially saying when you don't have the border map information, there's a parameters, for example, in alpha, beta, porosity, in a way that actually works out to capture the discharge dynamic. So it's related to, for example, there are so many different parameters, so it has itself working out in a way that still capture discharge. So I don't think you can say the difference is really because with or without border map. Or without.
In fact, did you show us anything that makes it look like it was better with the border map?
One thing is from this part, with the border, the parameter value will be close to the the physically meanings. This is one. Another is the.
I don't understand what you said.
For example, like Dr. Lee mentioned, if we change the case with the border to without border, we still need to change those parameter value, follow the difference from Shale Hills to Garner Run, which means the one without border, the parameter in that cases need to tune themselves and pretend there is a there is a macropore there. There is a macropore.
So I'm going to ask a question, but I think I might help answer Sue's question. So what happened was, especially even before we did our fieldwork last summer, and Yuning had presented and said, oh, Garner Run almost matches what we observed, but it looks like we need to make macropores a bigger factor here. And that's essentially what Dacheng is showing in his sort of self-calibrating model outputs. He's searching for the best fitting parameters, and what he's finding is, oh, gee, look, we have like these macropores that need to be really pumping water through the system, because that's what his outputs say makes the model fit best. What we did with our boulder map was say, I think we know what the macropores should be doing, and what Dacheng found was that the model's best fit and our best intuitive, field-worky guess ended up being quite similar. Whereas a model output, you have no physical meaning behind those parameters that you tuned, right? Because like last all hands, Yuning was like, oh, but like maybe we can make the macropores deeper, maybe we can make them bigger. And I was sitting here like, maybe, okay, let's go dig a hole and find out. And that's essentially what we did. And so I think this is actually telling us that field observations add necessary physical meaning to otherwise nebulous model best fits.
Yes, thank you, Jean-Marie. And also,
oh, sorry. So my question was the blue dots on the DMAC, KMAX. Those we didn't guess those though, correct? Pim is still tuning for the blue dots. Right?
yeah, they're blue.
Pim is
Yeah.
still tuning those, but so that's really those are pretty close.
Yeah,
right?
they are pretty close.
That's pretty good. So I mean, what happened was the model without our map still guessed well, but we as sort of scientists can't say what it means unless we can put this right there and say, oh, so it's the distribution and amount of boulders in this landscape that seem to be a first order control on what produces a best fitting model.
Yeah, we can say in that way.
Okay. Yeah, I don't know if it's working. It's a low battery and then it died.
I know, it's a low battery and then it goes away. That means either.
I have spares.
What?
I have spares if we need it.
How can I tell if it's working? I have no idea. So one of the things we're going to do, and I think Callum was supposed to do this, is upscale the model for the whole watershed. And so from that point of view, and from what Joan Marie just said, a good place to end your talk would be about upscaling, right? You could say anywhere where we have boulders, sandstone, we should use parameters that look like that. Or like, how would you say that? Like, what would you tell Callum to do to upscale based on what you've learned? Is that understandable?
Yeah. For my case, yes, I believe we can use the. You may remember from here we noticed that the pre-calibrated parameter value already give us some important information. So the one that we found the transferability test is not good is because we do have the lithology difference between Shale Hills and Garner Run. So when we do the upscaling, I would suggest the coefficient, the calibration coefficient for all the Garner Run has a similar sets. And for all the shale, or for all the sandstone have the similar sets, and for shale has the same one. If we do need the limestone or other part, we can redo these processes and get another sets for all that lithology. That is what we found. Yeah.
So where do you think the complication is going to come here? For instance, when we start modeling this whole farm catchment that we're looking at, or this. Yeah, so where does the complication come from here when we're moving to talking about this coal farm catchment that we're modeling, which is a mixed lithology? It's shale and limestone. Is that going to be an issue if we try to do a process like this there, since it's not monolithological?
I think so. Other than use this 6 parameter to be tuned, we can choose both soil one and the vegetation related one. For example, something changing the evapotranspiration, changing the leaf. So we tune those parameters together and get new accepted runs. Compare the parameter difference, both vegetation related and soil related. I think the story will be inside there.
Related to that, so you started your talk by saying topography is the main control.
Yeah, that may control as well. Yeah.
Elevation changes. So when you move down, and we're looking at both of these and headwater catchments, so if you're upscaling down into the Shavers Creek outlet in the valleys, can you apply the same? I feel like you have complications even though you shale bedrock, applying the same parameters when you're in the valley versus, or do you just use elevation data?
I think just use the elevation data from LiDAR or from an EPA is okay, yeah.
And the soil maps reflect.
Soil Sergo maps reflect hill slope position. When people classify soils, they give it like, oh, this is a ridgetop soil, this is a mid-slope soil, this is a valley soil. So perhaps some of the alpha, beta parameters that will be derived from Sergo maps reflect hill slope position inherently. Does that make sense? Right. But if someone has mapped that, soil maps are weird that way in that they account for gradient on the slope at which they are measuring. So there is like a double elevation aspect to PIM. So that's how elevation comes into play.
So I remember when we were over in Ag Sci talking about the fact that we didn't have anybody doing soil mapping, and there was some way that we were going to come up with, soil parameters without having done a lot of soil mapping. And Tess was very persuasive about how we were going to do this, but I can't remember what it was. Are we doing it? Is that what we're doing now, or have we not done what Tess was arguing for at that meeting? Or maybe everybody's confused about what I'm referring to.
So the question was if we can figure out soil parameters.
So I'm not remembering the exact conversation. Is the idea that we would use model outputs of PIM to make good guesses about soil parameters without measuring them? Is that what you're saying?
Well, I just remember we were worried because no one was thinking that they could map the whole thing and measure the mixed parameters and this
Right.
and the other. And Tess argued that there was another way to do it. And I'm just wondering, is that what we're doing?
No. Hi, Tess.
So ask me.
Oh, that's alpha beta. Yes. Yes. So like we were kind of what Dacheng was saying before is that the model outputs guessed fairly well, but we didn't know, we could not, how do you validate a model? Well, you compare it to data that you observe in the real world, and that's essentially what we've done by adding the boulder map and saying, I think this is the physical meaning behind, we need macropores that are, the ratio, the diameter, and I can't remember what you said, but maybe.
That's great. So we've come a long way. That was like a year ago, I think, when we talked about that. Should we thank you again, or are there more questions?
Thank you.